Hello, this is Adam Buell, and I'm going to be presenting my final project, the video section. So here's my original unanswered problem. The first step part of it is going to be a synthesis problem with the reactants of sulfuric acid, HBr, potassium hydroxide, bromine, and then water. The second part of my question is going to say, it says, label your molecules from the synthesis reaction by their functional groups, IMFs, and use net dipoles to determine the polarity of each molecule. So every molecule that I use from the synthesis, I need to give its intermolecular forces. I need to draw out any net dipoles. I need to label any functional groups, and then I have to name the if it's polar or not polar. So here's just the completed synthesis part. So the very first step is going to be a acid catalyzed dehydration. So first, the OH group is going to be taking a hydrogen from the sulfuric acid, making it H2O, and that makes it a good enough leaving group to where it can leave. And then one of the hydrogens from the adjacent carbons are going to be taken off, creating a double bond with the carbon that the water molecule just left. So because both of the adjacent carbons are both disubstituted, it can go to either one and you could have multiple products. But for the sake of this video, I just went ahead and did the double bond between the carbon that has the longer chain to it. So then, and then also this comes from chapter 2. This is also an example of an acid-base reaction. So the hydroxide is going to be acting as the base in this scenario, while the sulfuric acid is acting as an acid. And it's going to be giving one of its hydrogens to the hydroxide, which is going to be accepting the hydrogen, which is a perfect definition of a Bronsted-Lowry base, thus a acid-base reaction. So I guess you could just say the acid catalyzed dehydration of the alcohol is an acid-base reaction. So next, I should also probably say that's an E1 reaction, meaning that there's possible carbocation substitution, which in this case, we don't have any of that. And then it also follows Zasev's rule, which, like I said, the two disubstituted, so they're the same deal. Oops. So next we have a hydrohalogenation. And from this, we also have carbocation rearrangement. So, and again, the carbocation would go to which one is the more substituted, but since they're the same, so I put the carbocation at the this carbon right here. And we do have carbocation rearrangement. So the carbocation would go to the tri-substituted carbon that's adjacent to it. And this would just kick off a hydrogen for that, for the carbon that it's leaving. So then that would give us, that's why the bromine would be connected to the carbon that's adjacent to the double bond. And then this would also give us stereoisomers, which comes from chapter 5. I should have probably said the hydrohalogenation comes from chapter 10, and then the acid catalyzed dehydration comes from chapter 9. But then we come down to chapter 5 because we have stereoisomers. And that's why we have this plus and minus sign right here, because that indicates that this is a stereoisomer. And that's because we had a carbocation rearrangement. So since it happens in multiple steps, the bromine can add from either side. So you will get a molecule with the bromine facing out and facing in, signified by the plus minus sign right here. So you need to have knowledge of chiral centers to know about the stereochemistry of this molecule. So to have a chiral center, a carbon has to have 4 different substituents, anything from hydrogen, pretty much, anything. So this chiral center right here, this carbon, has 4 different groups. It has an ethyl group, a methyl group, a butyl group, and a bromine group, making it a chiral center. So that chiral center, we'd have to show with the stereochemistry. So, but like I said, the plus minus says that it's both. So that means the bromine could be facing out or sticking in. So next we have the strong nucleophile elimination reaction. So if we need knowledge from chapter 6 of what a strong nucleophile is, and we need to know whether if it's a strong nucleophile, an electrophile, or weak nucleophile, or say, because if it's a weak nucleophile, then we would have to do an E1 reaction rather than an E2. And then there's possible carbocation rearrangement, so you can get a completely different answer. So we need to know that it's a strong nucleophile. The KOH is going to be our strong nucleophile, and it's going to be going through an E2 reaction. And this also follows Zaysev's rule, which we get from chapter 8, and the elimination is from chapter 8 as well. So the bromine would be leaving. At the same time, the strong nucleophile is going to be grabbing one of the hydrogens from the adjacent carbons. And Zaysev's rule says we have to grab one of those hydrogens from the most substituted. So this methyl group, we can count that out. And then it's just the ethyl group and the butyl group. And they're both the same substituted. So I just went with the ethyl group, or I'm sorry, the butyl group, just for the sake of the problem, but you could have either one. So next we have our halohydrin formation that we also get from chapter 10. So this is just so the double bond, the two carbons that are adjacent, that are connected to the double bond, one of them will get the halogen and the other one will get an alcohol. So the halogen is actually going to go to the least substituted carbon. In this case, is going to be this one right here. So our bromine is going to go up there, and then our alcohol is going to go to our more substituted carbon. And then the last thing for the halohydrin formation, the halogen and the alcohol have to be anti to each other. So that's why the bromine is facing out and the alcohol is going in. It could have been either way. The bromine could have been going in and the alcohol could have been facing out as well, just as long as they're anti to each other. All righty. So that brings us to the next question. Label your molecules from the synthesis reaction by their functional groups, IMFs, and use net dipoles to determine the polarity of each molecule. So the first one is the one that we were given. And we have an alkane right here because it's just carbon to hydrogen bonds, or I'm sorry, just carbon to carbon single bonds. We don't have any double bonds. And then we have our net dipole right here between the carbon and the oxygen. So the electron density is actually going to be in the oxygen's favor and not the carbon, because the oxygen is more electronegative. And that's what this net dipole tells us. So that net dipole also lets us know what kind of, whether it's going to be polar or not. So this is going to be polar, and that brings me to the IMFs. This one has London dispersion, dipole-dipole, and hydrogen bonding. If something has hydrogen bonding, it's going to have everything. It's going to have dipole-dipole and London dispersion. And yeah, so the uneven density of the electrons is what makes this molecule polar. So next we have our alkene. So an alkene, it just needs one carbon-carbon double bond to be considered an alkene. So that's what this one is. And this is just London dispersion forces because it is just carbons and hydrogens in here. And that because it's London dispersion, there's no net dipoles, this molecule is going to be nonpolar. So next down here, we have an alkane, and we also have an alkyl halide group, which is just a halogen bonded to a carbon. So we have our net dipole between that bromine and the carbon. Electron density is going to be favoring the bromine. So just like in number one, or not just like in number one. So number one has hydrogen bonding. So hydrogen bonding is a hydrogen bonded to one of three molecules, oxygen, nitrogen, or fluorine. And that's like the strongest intermolecular force that we know of so far. And number three does not have that. So it has hydrogen carbon bonding, but that's not hydrogen bonding. So we just have London dispersion and dipole-dipole forces. And this molecule is also polar because all it takes is one net dipole to make the electron density uneven, and then it's going to be polar. So next we have our, alkene. So just like the other alkene, we just have London dispersion forces because all we have is carbon-hydrogen bonds, making this bond unpolar. And then next is going to be our the last product from the synthesis reaction. It's going to be an alkane because there's no double carbon bonds. We're also going to have an alkyl halide between that carbon and the bromine and an alcohol. So we have two net dipoles on this one. We have a net dipole between the carbon and the bromine, and a net dipole between the oxygen and the carbon. So this one is going to be polar as well. So it could be kind of tricky because the way for a molecule to be nonpolar, even if it has net dipole poles, is if the poles are symmetrical in the different directions. And I was kind of confused about this one because bromine's facing out, bromine's facing out, oxygen's facing in. So maybe they would, but it has to be more symmetrical. Since this isn't symmetrical, it is still going to be polar. And this one has hydrogen bonding, which means it's also going to have dipole-dipole and London dispersion effects. And that is going to be the conclusion of my video presentation. I don't think I am forgetting anything. And yeah, so that's going to be all. Thank you.